and welcome to the Transformations Masterclass. Let's get into it. Now we say the graph of a function has been transformed geometrically when it goes through a change in position, size, shape, or orientation. So we have different types of transformations, namely translations, reflections, rotations, shear, stretch, and enlargement. Now, for the first three transformations, we call them isometries because the size and the shape of the object is maintained. For the last three transformations, the size and or shape is not necessarily maintained. Now, for the purpose of the current syllabus, we shall be focusing on three transformations of functions. That's translations, reflections, and stretches. Let's talk about translations. Now, a translation or a shift occurs when an object is displaced such that it moves in a straight line. Now, translations can be represented by a column vector xy, where x represents the horizontal displacement and y represents the vertical displacement. So let's talk about vertical translations. Now, the graph of y is equal to f of x plus a is a vertical translation of the graph y is equal to f of x by the vector 0, a. So if a is positive, it means the graph will shift upwards by a units. And if a is negative, it means that the graph will shift downwards by a units. So we can have an example. Here, I'd want you to consider the graph y is equal to f of x shown. Now we can transform this graph to form the graph y is equal to f of x plus k, where k is a positive constant, through a translation. So the matrix representing this translation will be 0, k. So the new graph, therefore, will be this graph here, which is a shift of the original graph by k units upwards. Now we can also sketch the graph of y is equal to f of x minus k, where k is a positive constant, as being this graph. And since in this case we have negative k, it means the graph shifts downwards by k units. So that is something very important for you to know. Let's have an example. Now you're asked to make a sketch of the graph y is equal to x squared plus 2. Now the graph that you know is the graph of y is equal to x squared, which has a minimum point at the origin, 0, 0. Now this graph is your original graph. That's your y is equal to f of x. Now to draw the graph of y is equal to x squared plus 2, it means that in function notation, that's the graph of y is equal to f of x plus 2, which represents a translation of vector 0, 2. So the graph shifts upwards by 2 units. So the sketch of the graph y is equal to x squared plus 2 is this one here. Let's talk about horizontal translations. Now the graph of y is equal to f of x plus a is a horizontal translation of the graph y is equal to f of x by the vector negative a, 0. So that means that if a is positive, the graph shifts to the left, that is in the negative x direction by a units. And if a is negative, it means that the graph shifts to the right, that is parallel to the x-axis by a units. Here's an example. Here we're asked to sketch the graph y is equal to x plus 3 all squared. Now, the graph we know is the graph of y is equal to x squared. And for the graph of y is equal to x plus 3 all squared, in function notation, it would be the graph of y is equal to f of x plus 3. And since 3 here is positive, it means the graph should shift to the left by 3 units. So the graph of y is equal to x plus 3 squared should therefore be this one, which represents a shift of the original graph parallel to the x-axis in the negative direction. So let's have a summary. We're saying the graph of y is equal to f of x plus a is represented by the matrix 0a and is a shift by a units upwards parallel to the y-axis. The graph of y is equal to f of x minus a is represented by the matrix 0 and negative a and is a shift of the graph of f of x downwards by a units. The graph of y is equal to f of x plus a is represented by the matrix negative a 0 and is a translation or shift of the original f of x graph in the negative direction by a units. Lastly, the graph of y is equal to f of x minus a is represented by the vector a0 and it is a translation or shift of the original graph y is equal to f of x in the positive x direction by a units. And this is all provided a is a positive constant. So let's take a look at a few examples, starting with this one here. And it says the curve y is equal to x squared plus 3x plus 4 is translated by 2, 0. Find and simplify the equation of the translated curve. All right, so here we can see a translation, and it's essentially a horizontal translation by 2 units. So it's basically 2 units to the right. And if we let f of x be equal to x squared plus 3x plus 4, then after this translation, we should be having f of x minus 2. So this is how we represent a translation of 2 units to the right. It's f of x minus 2, which essentially will be x minus 2 squared plus 3 of x minus 2, and that's plus 4. And this is going to give us x squared minus 4x plus 4, and that's going to be plus 3x minus 6, expanding the brackets, and plus 4. And eventually we will get x squared, then minus 4x plus 3x is minus x, then plus 2 if we simplify it. So the equation of the translated curve, okay, equation of translated curve is going to be y is equal to x squared minus x plus 2. So that's how we answer this particular question. Let's move on to another one. Here the question says, the curve with the equation y is equal to x squared plus 2x minus 5 is translated by negative 1, 3. Find the equation of the translated curve, giving your answer in the form y is equal to ax squared plus bx plus c. Right, so I'm going to say let f of x be equal to x squared plus 2x minus 5. Now, these translations can be written in function notation, right? These are a horizontal translation by negative 1. We write that as f of x plus 1. Remember, if it is a horizontal translation, then you use the opposite sign. Okay, so if it's minus 1, if it's going to the left by 1 unit, it means that in function notation, you have to put a plus 1. So basically, that's how it works. And the other one here represents a vertical translation by 3 units. So essentially, it's going up by 3 units. So it's 3 units up. So we write that as plus 3. Right, so this here is the function notation representing the translations. So that's going to be, therefore, for x, we put x plus 1. So that's x plus 1 squared plus 2 of x plus 1. We have the minus 5 already, and plus 3, since we are adding 3 to the function. So expanding, that gives us x squared plus 2x plus 1, and that's plus 2x plus 2. and that's minus 5 plus 3, which therefore gives us x squared, and that's going to be plus 4x, then plus 1 if we simplify it. So we can therefore say that the equation of the translated curve is y is equal to x squared plus 4x plus 1. So that's how we answer this particular question. Here's another question, and it says, express x squared plus 6x plus 5 in the form x plus a squared plus b, where a and b are constants. Or so x squared plus 6x plus 5 will be, if we complete the square, x plus 3 squared minus 3 squared plus 5. Now, this is going to give us x plus 3 squared, and that's minus 9 plus 5, which is minus 4. So that is the answer. And on part B, they say the curve with the equation y is equal to x squared is transformed onto the curve y is equal to x squared plus 6x plus 5. Describe fully the transformations involved. So they're saying y is equal to x squared is being transformed onto this, which we got as x plus 3 squared minus 4, x plus 3 squared minus 4. So essentially what's going on is, if this is f of x, okay, if this is f of x, then in function notation, this should be f of x plus 3 and then minus 4. And I think you can see that both transformations are translations, right? So therefore, the transformations are translations. And for this, that's minus 3. And this is a vertical translation, minus 4. So this here is the answer. So that's how we answer these particular questions. So at this point, we'd want to talk about reflections. Now we know that a reflection occurs where a point is a mirror image of the object, and that's about a given mirror line. So the graph of y is equal to negative f of x represents a reflection of the graph y is equal to f of x in the x-axis. So say this is y is equal to f of x, then the graph of y is equal to negative f of x would be a reflection in the x-axis, so it would produce this graph. Next, the graph of y is equal to f of negative x is a reflection of the graph of y is equal to f of x in the y-axis. So if this is your y is equal to f of x, and you want to draw the graph of y is equal to f of negative x, then it would come out as this graph reflected in the y-axis. Let's take a look at a few examples. So this question here says, in each parts A, B, and C, the graph shown with solid lines has equation y is equal to f of x. The graph shown with broken lines is a transformation of y is equal to f of x. So they say we should state in terms of f the equation of the graph shown with broken lines. Okay, so I think you can see what's going on here. This graph, y is equal to f of x, is being transformed onto this graph. And I would like to think you can see that the graph with broken lines is actually a mirror image of the graph of y is equal to f of x, with the mirror line being the y-axis. Okay, so they're actually mirror images of each other, and the y-axis being the mirror line. And such a reflection means that the transformed graph should just be y is equal to f of negative x. So that's how we write, in terms of f, the equation of the graph with broken lines after the reflection. Let's have another example. Here the question says the graph of y is equal to f of x is transformed to the graph y is equal to 3 minus f of x. Describe fully, in the correct order, the transformations that have been combined. All right. So here, if you look at y is equal to 3 minus f of x, right? This can also be written as y is equal to minus f of x plus 3. You can clearly see that we have a reflection here, okay? And this is in the x-axis. And the plus 3 means translation, right? That's a translation, and well, that's 0, 3 essentially. So these are the two transformations, okay? The first one is going to be the reflection in the x-axis, or you can say the x-axis is the mirror line. And the second transformation is the translation and represented by the matrix 0, 3. And that's basically how we answer that particular question. Next, we want to talk about stretch. Now, a stretch occurs when all the points on the graph y is equal to f of x are moved towards or away from either the x-axis or the y-axis. Now, we have vertical stretches. Now, for vertical stretches, we are saying the graph of y is equal to a of f of x is a vertical stretch of y is equal to f of x by factor a. So if this is your y is equal to f of x, then the graph of y is equal to a of f of x, where a is a positive integer greater than 1, would be like this. So essentially, we multiply all the y coordinates by a to produce the image. Next, we can talk of horizontal stretches, where the graph of y is equal to f of ax is a horizontal stretch of the graph y is equal to f of x by scale factor 1 over a. So I'd want you to observe this graph of y is equal to f of x and this graph, which is y is equal to f of 2x. And I think you can see that it has shrunk horizontal wise. And essentially what we do is we multiply the x coordinates by the scale factor, that's 1 over a. So let's look at a few examples. So this question here says, the equation of a curve is y is equal to x squared minus 8x plus 5. So on part A, find the coordinates of the minimum point of the curve. So we have y is equal to x squared minus 8x plus 5. If we complete the square, it becomes here x minus 4 squared, and that's minus 4 squared and is plus 5, which comes out as bracket x minus 4 squared, and that's minus 16 plus 5, which is minus 11. So therefore, the coordinates of the minimum point are going to be, we take 4 here, so 4 and minus 11 here. So that's what we'll be having for part A. On part B, the curve is stretched by a factor of 2 parallel to the y-axis and then translated by 4, 1. So find the coordinates of the minimum point of the transformed curve. All right. So remember the minimum point is 4. Okay, so that's 4 and negative 11. After the first transformation, we know that if it is stretched parallel to the y-axis by 2 units, we multiply the y coordinates by 2. So after the first transformation, we'll be having 4 and minus 22. All right. Now we apply the second set of transformations, that's number 2, which are translations. So this is an x translation where the graph shifts to the right by 4 units. So we will add 4 to the x coordinate, and now it becomes 8. And we also have 1, which means it's a vertical translation. This is x and this is y by 1 unit. So we're also going to add 1 to this, all right? So it becomes minus 21. So what we have here is, therefore, the new minimum point. That's 8 and negative 21. And that's how we answer this question. Let's go to another one. Here, we had done part A earlier, but we want to focus on part B. Remember, they'd said here that the graph with solid lines is y is equal to f of x, and the graph with broken lines is the transformation of y is equal to f of x. And now here on part B, they say we should state in terms of f the equation of the graph shown with broken lines. Right, so I think you can see that we essentially have a vertical stretch going on. If you look at the full height of the original graph, which is 2 units, and the full height of the one in broken lines is actually now 4 units, you can actually see that the graph has been stretched by a factor of 2. All right, so that's essentially what has happened. It's basically a vertical stretch. So stretch parallel to y-axis, and that's by factor 2. But here they want, in terms of f, the function notation for that, which would simply be 2 of f of x. That's essentially what's going on here. So that's how we can answer that particular question. We're going to have one more question, and it says the graph with the equation y is equal to f of x is transformed to the graph y is equal to g of x by a stretch in the x direction with factor 0.5. So it's a stretch in the x direction factor 0.5 followed by a translation of vector 0, 1. So these are the two transformations going on, all right? Okay, so the question now says the diagram shows the graph of y is equal to f of x, and on the diagram sketch the graph of g of x. Right, so we have two transformations. The first one is a stretch, all right, parallel to x-axis, and the factor, according to what's been given, is 0.5. So if the factor is 0.5, it means we're going to multiply the x-coordinates by 0.5, essentially by a half. Here, the x-coordinate is 0, so 0 times 0.5 is still 0. And this point has an x value of 1, right? So 1 times a half is a half, so it will be transformed onto this point. This point has an x value of 2, so 2 times a half is 1, so it will be transformed onto this point. This point is a 3. 3 times a half is 1.5. So it is being transformed onto this point. And this point has an x value of 4. 4 times a half is 2. So it is being transformed onto here. So the new graph after the stretch should be like this. That's the graph. All right. And then it undergoes the second transformation, which is a translation by 0, 1, which means this graph is going to shift upwards by 1 unit, like this. So what we now have is g of x, this new graph in red. And that's basically how we do it right here. Now on part B, they say we should find an expression for g of x in terms of f of x. Okay, so these are the two transformations. Let me just put this down here for guidance. So an expression for g of x in terms of f of x, well, the transformations that went by were the stretch of factor 0.5. So that's like f of 1 over 0.5 is 2, so 2x. And this vertical translation is represented by plus 1. All right, so this is how it is, okay? This is the function notation for g of x in terms of f. That's how we would express it. Now, how did I get this to? Okay, I know some of you missed that. Remember, if you have f of ax, your scale factor will be 1 over a. So that's exactly what I did. If we have 0.5 as the scale factor, it means when we write it inside here, we say 1 over 0.5, which is 2. So that's why there's a 2 right on here. So basically that's how we do it. So at this point, we'd want to talk about combined transformations. Now, I'd want you to consider the general transformation formula y is equal to a of f of b of x minus c plus d. So this is the general transformation formula. And now, in order to determine the sequence of transformations represented by this general transformation formula, you have to start from inside the brackets going to the outside. So the first transformation here is represented by minus c. That's a translation of vector c0. The second transformation would be represented by b, and that's a horizontal stretch by vector 1 over b. The next transformation is the one represented by a, and that's a vertical stretch of vector a. The last transformation here is the one represented by d, which is a translation of vector 0d. Let's have a few examples. Here the question says, the graph of y is equal to f of x is transformed to the graph of y is equal to 1 plus f of half of x. Describe fully the two single transformations which have been combined to give the resulting transformation. All right, so here we are saying for y is equal to 1 plus f of a half of x, the first transformation should be the one represented by a half. That's the one inside the bracket. And the second transformation is the one represented by the term that is outside of the bracket. Right, so we're going to say here, number one, okay, this is a half. So that's a horizontal stretch. So I'll say here, it's a stretch and parallel to the x-axis. And the scale factor is 1 over a half, which is 2. Then the second transformation, the plus 1, represents a translation. And that's a translation of in the y-axis, so it's 0, 1. So these are the two transformations going on right here. So let's move on to the next question. And here it says, the graph of y is equal to f of x is transformed by the graph y is equal to 2 of f of x minus 1. So they say describe fully the two single transformations which have been combined to give the resulting transformation. All right, so basically we're starting from inside, okay, where f of x minus 1 represents a translation, and that's a translation of 1 unit, so 1, 0. Okay. The second transformation, number 2, is what's represented by 2, which is a stretch. So I would say a stretch and parallel to the y-axis. And the scale factor is 2. That's how we answer that particular question. Let's move on. Oh, there's a part B. Okay, part B says, the curve y is equal to sine of 2x minus 5x is reflected in the y-axis and then stretched by a factor of a third in the x direction. Write down the equation of the transformed curve. All right, so I'll say here, let f of x be equal to sine 2x minus 5x. So this is the first transformation, a reflection in the y-axis. All right, so under the first transformation, we will be getting f of negative x. Okay, that's how we represent a reflection in the y-axis, which basically is sine of negative 2x minus 5 of negative x. So basically, sine of negative 2x is like minus sine 2x. So 2x here, and that's plus 5x. The second transformation is a stretch, right, of scale factor of a third. So under the second transformation, in set notation, that would be f of 3 of negative x, right? So essentially, we are saying that's going to be minus sine of 2 of 3x, and that's plus 5 of 3x, right? So that's going to give us minus sine of 6x plus 15x. So that's going to be the answer here to part B. Let's have one more example. And the question here says the graph of y is equal to f of x is transformed to the graph of y is equal to f of 2x minus 3. So on A, describe fully the two single transformations that have been combined to give the resulting transformation. All right, so here, the first transformation is represented by the 2. That's a horizontal stretch. So I'll say here, it's a stretch parallel to the x-axis, and the factor is a half. And the next one would be represented by the minus 3. That's basically a translation, and it's a translation with vector 0 and negative 3. So basically those are the two transformations going on right here. So let's go on to part B, which says the point P of coordinates 5, 6 lies on the transformed curve y is equal to f of 2x minus 3. So state the coordinates of the corresponding point on the original curve y is equal to f of x. All right, so what they're saying is we've got f of x and we've got the transformed curve f of 2x minus 3. So we have a point which is on the transformed curve, which is 5, 6. So we want to know what the original point was before the transformation went on. So basically, the transformation was in two parts, right? The first one was a stretch and factor of a half. All right. That was the first transformation. The second one was a translation of 0, negative 3. So that's number 2. So to move from here back to here, we have to do the reverse. Okay. So the reverse of number 2, the reverse of a translation 0, negative 3 would be a translation 0, 3. So we'll be adding 3 to the y coordinate. So it's 5, 9. And then when we then go on back, the reverse of transformation 1, which was a stretch of a factor of a half, where we would multiply the x coordinates by half. Here we'll multiply the x coordinate by 2 as the reverse. So multiplying this by 2 would give us 10. So 10, 9. So essentially, the original point was 10, 9. Okay, 10, 9. Sorry. 10, 9 is the answer. So that's how we do it for this particular question. So at this point, we want to look at a few more questions involving a sequence of transformations where the order with which the transformations were applied is important. Let's start with this question here, and it says, the curve y is equal to x squared is transformed to the curve y is equal to 4 of x minus 3 squared minus 8. Describe fully a sequence of transformations that have been combined, making clear the order in which the transformations have been applied. All right, so I'll start by saying let f of x be equal to x squared, which therefore means that the equation y is equal to 4 of x minus 3 squared minus 8 is in function notation equal to 4 of f of x minus 3 minus 8. All right, so which transformations are going on? Okay, we start from inside the bracket, and we have minus 3 representing a translation of vector 3, 0, right? Then we go outside where we have a stretch parallel to the y-axis and factor 4. Then the third transformation is a translation again of vector 0 and minus 8. So 1, 2, 3. That's the order in which the transformations were applied. Let's have another question. Question 21 says, a function f is defined by f of x is equal to x squared minus 2x plus 5 for x is an element of all real numbers. A sequence of transformations is applied in the following order of the graph y is equal to f of x to give the graph of y is equal to g of x. So we have a stretch, okay, parallel to the x-axis with scale factor half, a reflection in the y-axis, stretch parallel to the y-axis with scale factor 3. So find g of x, giving you answer in this form, okay? So we have, we're starting with the original function f of x. And if we apply transformation 1, okay, transformation 1, which is a stretch parallel to the x-axis with factor half, then that's f of 2x. If we apply transformation 2, which is a reflection in the y-axis, it becomes f of minus of 2x. So basically minus 2x. And then number 3, if we apply number 3, that would be a stretch parallel to the y-axis, vector 3. That's 3 of f of minus 2x, basically. So this is the graph we want. So since f of x is x squared minus 2x plus 5, actually 3 of f of negative 2x would be 3, and that's 3 of negative 2x squared minus 2 of negative 2x plus 5. So basically what we will be having is 3 of 4x squared plus 4x plus 5. So we would get the answer, final answer, to be 12x squared plus 12x plus 5. So that is the new function g of x. So g of x comes out as 12x squared plus 12x plus 5. All right, so that's how we do it for this particular question. Let's move on to the next one. The curve with equation y is equal to 8x squared minus k minus 1 is transformed to the curve with equation y is equal to h of x by the following sequence of transformations. A translation of 2, 3, that's the first transformation, number 1. Number 2 is a stretch in the y direction by scale factor k. And number 3 is a reflection in the x-axis. So they say we should find an expression for h of x in terms of x and k. All right, so I'll start by saying let f of x be equal to the 8x squared minus k minus 1, which therefore means that if we start with f of x, after the first transformation, which is a translation 2, 3, it will be f of x minus 2 plus 3. Then after the second transformation, okay, second transformation, number 2, it's a stretch parallel to the y-axis by scale factor k. So it becomes k of the f of x minus 2 plus 3 that we had. And after the third transformation, that's number 3 now, which is a reflection in the x-axis, it will be minus k of f of x minus 2 plus 3, right? So that's what h of x is. H of x is that. It's minus k, and that's of f of x minus 2 plus 3. This is just like minus k, and that's off. And for what's inside here, f of x minus 2 is 8 of x minus 2 squared minus k minus 1, and there's a plus 3 here. So basically that. So that's going to be equal to minus 8k of x minus 2 squared. Okay, so I've multiplied minus k by this. And I'm also going to multiply minus k by whatever we get from here, which is, well, minus k plus 2. So this can be written as minus 8k of x minus 2 squared plus k squared minus 2k. So this here is the answer. So at this point, we'd want to talk about transformation diagrams. And here we will specifically be looking at problems in which you are given the graph of an original function and the graph of the image produced by the function under a sequence of transformations. And from here, you're asked to describe the sequence of transformations that produced that image function. So we will be looking at a couple of examples, starting with this particular one. The question here says, in the diagram, the graph of y is equal to f of x is shown with solid lines. The graph shown with broken lines is a transformation of y is equal to f of x. So on part A, describe fully the two single transformations of y is equal to f of x that have been combined to give the resulting transformation. Now, to answer this type of questions, I am going to give you a method which will really help you for all type of problems of this kind. And I would like to call this the reflect, stretch, translate approach. So in this particular case, we're saying reflect, stretch, then translate. Okay, so translate here. So what this means is we will start by checking if for the transformation that's going on from here to here, is there any reflection going on? And apparently, I think you can see that it doesn't seem like the graph of y is equal to f of x was reflected in any way in order for it to produce the image. So I'll say that there is zero reflections going on here. Next, I'm going to check for stretches, and I'll start with the ones that are parallel to the x-axis, right? So x-axis and y-axis. Now, if you look at the horizontal width, the width of the original function, which is 2 units, and the width of the other v, I think you can see that they are both 2 units, which means that there is 0 stretches, horizontal stretches happening here. Let's check the y stretches, the ones parallel to the y-axis. And the vertical height of the v is 1 unit. The vertical height of this image is 3 units, which means there is a vertical stretch going on by 3 units, factor of 3. So factor 3. All right. So that's the first transformation that I'm going to write here, which is a stretch parallel to the y-axis with a factor of 3. All right. So if we are going to apply this stretch on the original graph, if we take this point, which is a y value of 2, we would be multiplying it by the scale factor, which is 3. So 2 times 3 is 6. So the image is here. Then this point, which has an y value of 1 times 3, that's 3. So it'll be here. And this particular point, which is a y value of 2, 2 times 3 is 6. So its image will be here. So after the stretch, we will be having the graph like this. All right. Now from here, we go to the third, which is the translation, which means that this graph now needs to be translated. All right. So, and it moves to the right all the way up to here. All right. So how many units parallel to the x-axis is the translation here from 0.5 to 4.5. So that's the translation of 4 units. So the graph has to move 4 units to the right in order to produce the image. So I'll say that the second transformation is a translation of 4 units. So translation 40 would be the answer right here. So these are the 2 transformations. Okay. And that's how we do it. Let's have another example. Actually, there's a part B. Let's just answer part B before we go to the next question. So in part B, it says, state in terms of y, f and x, the equation of the graph with broken lines. All right, so this is now easy to do because we are considering the stretch of vector 3, so which is 3 of f of x, and the translation of 4 units parallel to the x-axis, positive direction. So it will be x minus 4 for this. So y is equal to 3 of f of x minus 4. So that's the answer to part B. Let's move on to the next question. And here it is. It says, the diagram shows graphs with equations y is equal to f of x and y is equal to g of x. All right. So describe fully a sequence of 2 transformations which transform the graph of y is equal to f of x to y is equal to g of x. All right, so like I said, reflect, stretch, translate. Let's start with checking if there's any reflections. And it doesn't seem like the graph of y is equal to f of x was reflected in any way to give the graph of g of x. So I'll say here that there is 0 reflections. Next, we check on the stretches. And on the stretches, let's start with the horizontal ones parallel to the x-axis. And for the ones that are parallel to the x-axis, it doesn't seem like there's any horizontal stretch, because if you check any comparable parts or line segments, this one has a horizontal width of, well, that's 2 units. This still has the same horizontal width. So it doesn't seem that there's any horizontal stretch going on. So I'll say 0 stretches parallel to the x-axis. Vertical stretches parallel to the y-axis are obviously there, right? And if you check on the height of this shape, vertical height, it's apparently 1, 2, 3, 4, 5, 6, 6 units. If you check at the vertical height of this other one, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 units. So there's actually a stretch vertically of vector 2. Okay, so vector 2. All right, so let's stretch the diagram. Actually, let's just write down that transformation. So number 1 is a stretch parallel to the y-axis, and we say vector 2. All right, so if we stretch this by vector 2, all right, going point by point, if we take this point and we the y value is -3 times 2 is -6, so it will be here. Then this point has a y value of -1 times 2 becomes -2, so it will go here. This point has a y value of 3 times 2 becomes 6, so it comes here. And this point is a y value of 2 again, 3 times 2, that's 6, so it'll be here. So after the stretch, the diagram will be like this. Now, we've done the stretch. Now comes the translation. it means that this graph will simply move to the left like this and produce the image, right? So that's a translation. Okay, let me write that down. Translation. And the vector is going to the left. That is part of the x-axis. So 0 on the y. And how many units are going to the left? That's apparently 6 units, right? If you take this point, 1, 2, 3, 4, 5, 6 to the left. So basically -6, 0. So these are the two transformations. Okay. So that's how we would answer this particular question. Okay, let's move on to another one. And here it is. And it says, the diagram shows the graph of y is equal to f of x, which consists of two straight lines, AB and BC. The lines A dash B dash and B dash C dash form the graph of y is equal to g of x, which is the result of applying a sequence of two transformations in either order to y is equal to f of x. State fully the two transformations. All right. Reflection, stretch, translation. It doesn't seem like there's any reflection. And as for the stretches, horizontal stretch, which is an X stretch, seems to be there, because if you look at the full width of horizontally of the original graph between A and C horizontally is 3 units. Then the full width from A dash to C dash is apparently 6 units. So it's a horizontal stretch of factor 2. Then vertically, if you look at the height, 2 units, and the height here, 2 units. So there's no vertical stretches. All right. So the first transformation I'm going to write here is that there is a stretch parallel to the x-axis with a factor, and that's a factor 2. Okay, so that's the first transformation. Okay, let's move on to looking at translations. All right, so I'm going to remove all this and let's now look at translations. But before we do, if we apply a stretch of factor 2 to the original graph, it will be like what? It will be like this point, which is a 1, becomes a 2 because we multiply by 2. The x value is a 1, so 1 times 2, it becomes 2. This point here has an x value of 2 times, multiply by that by 2, the x value becomes actually 4. Then this point has an x value of 4, so 4 times 2 becomes 8, so goes here. So after the horizontal stretch, this is the graph we will be having. And then from here, we can translate it downwards, right? And it goes to where it now is. So basically, the next transformation is a translation, and it's a translation where the graph goes down only by 2 units. So 0, -2, right? All right, so that's the second transformation, which is a translation 0, -2. So these are the two transformations that happen on here. Another example. Here it says, in the diagram, the graph with equation y is equal to f of x is shown with solid lines, and the graph with equation y is equal to g of x is shown with broken lines. So in A, describe fully a sequence of 3 transformations which transforms the graph of y is equal to f of x to the graph of y is equal to g of x. Right, so we're going to use the same approach, all right? You reflect, check for reflections, stretches, and finish with checking for translations. All right, so there seems to be a reflection here, and it's a reflection in the y-axis. So if we reflect the original function y is equal to f of x in the y-axis, it'll come out like this. So this is how it will be like. All right. So I'm just going to write that down. Reflection in the y-axis. All right. Next, what I'm going to do is I'm going to check for stretches, and horizontally, it doesn't seem like there's any stretch because the horizontal width of the original diagram, which is 4 units, is the same horizontal width the image has, still 4 units. So no horizontal stretches. So we're saying that for horizontal stretches, there's none. How about for vertical stretches? The original graph has a vertical height of 2 units. This one has a vertical height of 4 units. So there's clearly a vertical stretch going on of vector 2. All right. So I'll write that down. That's a stretch parallel to the y-axis, vector 2. All right. And I'm going to apply that stretch to the graph that we have. So for this point, it's at 3 times 2 becomes 6. This point is at 1 times 2 goes to 2. This point goes to 2. And this point has a y value of 2. Multiply that by 2 becomes 4. So it comes here. So the new diagram here is now like this. After the stretch, it now looks like this. And I'm going to erase this. And from here, it's now clear how the translation goes on, because this graph now needs to move by a unit in the negative x direction, all right? All right, so that's a translation of 1 unit in the negative x direction, and I'll write that down. That's a translation and negative 1, 0. So these are the 3 transformations. Part B then says, find an expression for g of x in the form a of f of bx plus c, where a, b, and c are integers. All right, so we started with the graph of y is equal to f of x. Then it underwent the first transformation. The first transformation was a reflection in the y-axis. So that's transformation 1. So it became negative of f of x. Actually, it's in the y-axis, so rather it has to be f of negative x. Then the second transformation was a stretch parallel to the y-axis. So that's number 2. So vector 2. So it's 2 of f of negative x. The third one is a translation negative 1, 0. So it's 2f of and negative, and that's of x plus 1, basically, which then gives us 2 of f of minus x minus 1, right? So that is the function g of x. It's 2f of minus x minus 1, and that's the answer here. That's how we do it. At this point, we'd want to talk about transformations of trigonometric graphs. So I have a few examples that we're going to use for this. Starting with this question here, it says the diagram shows the graph of y is equal to f of x, where f of x is equal to 3 over 2 of cosine of 2x plus a half for values of x ranging between 0 and pi. So on part A, they say we should state the range of f. All right, so here we are going to say for the range of f, range, remember, is the set of y values. And the transformations going on here, which would affect the y values, would be represented by 3 over 2. So basically, we're saying 3 over 2, and it's multiplying cosine of x, and the range of cosine of 2x, okay, as an individual function is plus or minus 1. Remember, for a normal cosine graph, y is equal to cosine x or cos of any multiple of x, the maximum minimum value is always plus and minus 1. But here it is being affected by a stretch of 3 over 2. So we are multiplying those two limits, plus and minus 1, by 3 over 2. And then there's a plus half, which means we then add a half, because this is a translation which also affects the y values, and therefore it affects the extreme values vertically for our function, and that's what's going to give us the range. So here we will get two values, okay? We'll say 3 over 2 of minus 1 plus a half, and this gives us, that's minus 3 over 2 plus a half, that's minus 2 over 2. So that's basically minus 1. And we have 3 over 2 of 1 plus a half, which is 2. So therefore, the range of f is going to be from minus 1 to 2. So this here is the answer. That's how we do it right here. Next we go on to the so we go on to the next part, which says a function g is such that g of x is equal to f of x plus k, where k is a positive constant. The x-axis is a tangent to the curve y is equal to g of x. So on B, they say state the value of k and hence describe fully the transformation that maps the curve y is equal to f of x onto g of x. Or so it's clearly a translation of vector k, and k is a positive constant, which means the graph goes vertically upwards until the x-axis is a tangent. So this is when this minimum point, which is at minus 1, remember the range is from minus 1 to 2, so which is from minus 1, when it moves such that it touches the x-axis and now makes it a tangent. Okay, so it is going to move upwards by basically 1 unit, which means that k is 1. All right, so we are saying that the value of k is 1, representing a translation upwards by 1 unit to make this graph have the x-axis as its tangent. Okay, and they also say, hence, describe fully the single transformation that maps f of x onto g of x. So the transformation is basically a translation represented by the vector 0 and 1. That's all it is, and that's how we answer part B. Then part C says, state the equation of the curve, which is a reflection of y is equal to f of x in the x-axis. Give your answer in the form y is equal to a cos 2x plus b. So basically, our f of x is the original function we got right on here, which is 3 over 2 of cosine of 2x plus a half. So that's 3 over 2 of cosine of 2x plus a half. All right, that's f of x. So after a reflection in the x-axis, what we will be having is negative f of x, basically, which is minus 3 over 2 of cosine of 2x minus a half. So this here is the answer. Okay, that's the equation of the curve. Let me write it down here. So therefore, it's y is equal to minus 3 over 2 of cosine of 2x minus a half. That's what we'll be having right here. Let's move on. Now we're on question 3. And question 3 says, the functions f and g are such that f of x is equal to 2 minus 3 sine of 2x for values of x ranging between 0 and pi. G of x is equal to negative 2 of f of x for values of x ranging between 0 and pi. So on A here, they say we should state the ranges of f and g. Or so for f, we are going to get the range as 2 minus 3, and the range of sine to x is plus and minus 1, basically. Right, so we have 2 minus 3 of minus 1 and 2 minus 3 of 1. right? Which will give us right here 2 plus 3, so that's 5 as one limit, and here is minus 1. So the range of f is from -1 to 5. Okay, so let me just create space for this, or let me just write it here. Therefore, range of f is from -1 to 5. Okay, so I'm going to remove these workings because of the limited space we have. Let's go to the function g. The function g is negative of 2 of f of x, right? Which is such that it's minus 2 of f of x, which is 2 minus 3 of plus or minus 1, basically. Right, so we had gotten that the range of this function is -1 and 5. So essentially, we're just saying for the range, it's going to be -2 of -1 and -2 of 5. So therefore, the range of G is going to be from the list is going to be -10, right? So from -10 to, this gives us 2 to 2. So these are the answers right here. Let's move on to the next part, which says the diagram shows the graph y is equal to f of x, right? So that's what we have. And on part B, it says, sketch on this diagram the graph of y is equal to g of x, right? So the graph of y is equal to g of x is essentially represented by -2 of f of x, which means that there's a reflection in the x-axis, and there's also a stretch parallel to y-axis, and with scale factor of 2. So these are the two transformations here. So it means that we're going to reflect this graph in the x-axis, right? If we do so, then we'll be having something like this. Okay, so I've reflected it in the x-axis, and then I stretch it parallel to the y-axis. So it's now a little bit stretched. Okay, this is the graph. Okay, y is equal to g of x. That's the answer. Let's go on to the next part, which says the function h is such that h of x is equal to g of x plus pi. Describe fully a sequence of transformations that maps f of x onto, f of x onto h of x. So essentially, we are saying that starting from f of x, the transformations that happen, okay, if you go back, you can see that from f of x to g of x, we had two transformations. I've actually written them down here. These are the first two transformations that we are going to state. Okay, so I'll remove this. So the first one is a reflection in the x-axis. The second one we said was a stretch parallel to the y-axis by scale factor 2. So stretch parallel to the y-axis with a factor of 2. So yeah. Then there's also the part g of x plus pi, which technically is a translation, right? And the vector is 0 and minus pi. So these are that's the sequence of transformations mapping f of x onto h of x, really. All right, so that's how we do it. Let's have another question. And here it is. It says in the diagram, the lower curve has equation y is equal to cosine of theta. The upper curve shows the result of applying a combination of transformations to y is equal to cosine of theta. Find, in terms of cosine of a cosine function, the equation of the upper curve. The equation of the upper curve. Right, so we have a series of transformations mapping two graphs, all right? And we're going to use the reflect, stretch, and translate functionality or method I taught you earlier, right? So starting with the first graph, y is equal to cosine of x. I'm going to say here, let f of theta be equal to the cosine of theta, right? Let's look at if there is any reflection. If you look at the two graphs, it doesn't appear as if there has been any reflection. So I'll cancel out reflection. So no negative signs anywhere. Then there's obviously some stretches going on, some horizontal stretches, obviously. If you look at the original graph, this is the original graph, all right, but going all the way, but it appears to have been stretched, okay? It has a period here of 2 pi, but when it then goes to the other graph, it now has a period which is double that, which is 4 pi, which means there's a stretch of factor 2 really going on. So horizontally, there's a stretch of factor 2. I'll write here factor 2. So that means that the cosine graph here is now giving us cosine of half theta, because that's like f of a half theta. Oh dear, let me use the correct pen. F of a half theta is what represents a stretch of factor 2, which is cosine of half theta. So that's what we have right now. There is also a vertical stretch. If you look at the height from peak to trough, it's 2 units. And for the other graph, it's twice that, 4 units. So there's also a vertical stretch of factor 2. So basically, that's going to represent, okay, transforming will give us 2 of f of half theta, which is 2 cosine of half theta. All right. Now, we're going to check if there is any translations that have gone on. Okay, so I want you to look at this carefully. The original graph was like this, right? I'll just take the first period, the first part of it from 0 to 2 pi, and it was stretched horizontally. All right. So like this. After being stretched, it was also stretched vertically, right? So if I pick a point like this one, after being stretched vertically by a factor 2, 1 becomes 2. So it's now like this. And negative 1 times 2 becomes negative 2. So it goes down somewhere here. And this point is also at 1, but it also, after being translated, will now be somewhere at 2. So the stretch graph will now be more like this. All right. So this is how it is. All right. After these two transformations, this and this. So now it needs to move upwards in order for it to give us the image by how many units? From 2, it has to go up by 1, 2, 3. All right. It has to go up by 3 units. And if this graph goes up by 3 units, it will then fit onto the image. All right. So basically, that's how it is. So the translation is there. And this translation is a translation of a vector going upwards. That's 0, 3. Okay. So that's what we're dealing with, which means that after this, we will have the 2f of a half theta, and it's going to be plus 3. And that will give us the new graph as being 2 cosine of half theta and then plus 3. Okay, So I'll write that down. Okay, it's the cosine function is y is equal to 2 of cosine of half theta, and that's going to be plus 3. And that's your answer here. Let's move on to another question. And here we are. And it says, a curve has equation y is equal to 3 cosine of 2x plus 2 for values of x ranging between 0 and pi. So it says, state the greatest and least values of y. Or so that's 3 of the greatest and least value of cosine of 2x is plus or minus 1. And that's plus 2. All right. So that's 3 of minus 1 plus 2 and 3 of 1 plus 2. That's minus 1 here, and this is 5 here. So the greatest value is 5, and the least is equal to minus 1. That's how we do it. Then part B says we should sketch the graph of y is equal to 3 cosine of that. Okay, all right. Well, this is going to be like this. Okay, I'll have the vertical axis and the horizontal axis. We know that the normal, the cosine graph looks more like this, right? So it goes all the way up to 2 pi. Okay, up to 2 pi. That's the cosine graph. Y is equal to cosine of x. But with this transformation, it means that it's more like, if you write it in function notation, is 3 of f of 2x plus 2, where it was stretched by a factor of 2, actually a factor of a half, which means the period is now more like this, up to a half, a half of 2 pi, which is pi, and it undergoes a stretch and a translation where the least value will be minus 1 and the greatest value will be 5. So the graph will, I think, be more like this, where this is 5 and this is minus 1 and everything else doesn't matter. So this is the graph I'll come up with right here. All right. Let's move on to the next part. Part C, which says, by considering the straight line y is equal to kx, where k is a constant, state the number of solutions of the equation y is equal to 3 cosine of 2x plus 2 equals to kx for 0 to pi in each of the following cases. So the first case is when k is equal to negative 3. All right, so here we're going to make a sketch of y is equal to negative 3x and see how many times it would intercept this graph. All right, so y is equal to negative 3x would be a line that comes down like this. All right, so that's how it is. And it will, if you look at it in no wise, intercept this graph from 0 to pi. So therefore, I can say here we will have no solutions. Okay. And let's go to when k is equal to 1. It means it's y is equal to 1x. So y is equal to x. Now for y is equal to x, let me remove this one here. Y is equal to x would go like this. How sure are we that it will not intercept the curve twice, right? We know that this graph, let us consider this point, which is pi. All right, it would certainly go pass through a point pi and pi because y is equal to x. And the point pi and pi, we know that pi is 3.14, right? So it is less than 5. So the point pi and pi would be somewhere here. So if we have a proper graph, actually, it should also pass through a point pi and pi All right, pi is 3.142 and so on. So we can say that the graph y is equal to x will intercept the graph twice. Okay, I've just taken a point pi and pi, which we know for certain the graph is going to pass through, and therefore it will intersect twice. So I can say here two solutions. Then k is equal to 3, which means we have to draw the graph of y is equal to 3x, 3x. All right, which would be steeper than this graph that we have, right? So I'll erase this, and I can say here from my judgment, okay, if we remove this, that the line y is equal to 3x should go like this. All right, that's y is equal to 3x, because when x is equal to pi, y is equal to 3 pi, and 3 pi is greater than 9. So pi and something greater than 9, they would meet somewhere up there. So basically it intercepts once. So I would say here they'll only have one solution. So that's essentially how we would answer this particular question. Let's move on to the next one. Actually, there's a part D which says the functions f, g, and h are defined for x is an element of all real numbers by f of x is equal to this, and g of x is equal to this, and h of x equals to this. So they say here, describe fully a sequence of transformations that maps f of x onto g of x. All right, so here, all right, we are saying that g of x is equal to f of 2x plus 4. So this transformation should be a stretch parallel to the x-axis factor, and that's factor a half. That's the first transformation. And the second one would be represented by the 4. That's just a translation. That's a translation 0, 4, basically. So these are the two transformations that are going on right here. Let's move on to part A, which says describe fully a sequence of transformation that maps f of x onto h of x. All right, so h of x, according to what we've been given, is this 2 of f of x plus a half pi. So 2 of f of x plus a half pi. All right, so we start from inside. First transformation represented here is translation with a negative half pi, 0. Then the 2 represents a stretch, factor 2 parallel to y-axis. That's how we would answer that part. And that's how we do it right here.